Hi, everyone. Thank you for joining us. This is part of the Invited Speaker Series by the National University Transportation Center, TriDurLE. And today we unfortunately have something to announce, which is out of the ordinary of typical monthly webinars. So it is with a very heavy heart for me to announce that one of our site directors, Professor Wahid Uddin, had passed away due to COVID-19. And so we want to take this opportunity to, say a few words, and then we'll do a 1-minute silence in honor of his memory, and then we'll continue with the regular business of monthly webinar. So for those of you who don't know, Dr. Uddin is a professor of civil engineering at the University of Mississippi. He served as a pavement expert for the United Nations during the late 80s to 90s, early 90s. And he contributed to airport and highway pavement projects in the US and many other countries. He also served as the site director for this national UTC, TriDurLE, contributing his expertise in pavement engineering, asset management, and climate change adaptation. He, of course, had received numerous awards, including Best Alumnus Award from the University of Texas, Austin, and Lifetime Achievement Award from iSmartEye, International Society for Maintenance and Rehab of Transportation Infrastructures. He was actually one of the founding presidents. And Wahid was always a promoter and supporter of other people, and he'll be greatly missed. Now, with that, Michelle, let's do the 1-minute silence. Could you start a timer? And then I'll give it to you for, introduction of the speaker today.
Okay, thank you.
Thank you.
Okay, it's time to begin. Thank you, everyone, for that recognition of Dr. Uddin. So good morning, everyone, and welcome to our webinar. Our speaker today is Dr. Chris Pantelides. He's a structural engineer and fellow of the American Concrete Institute and professor in the Civil and Environmental Engineering Department at the University of Utah. He's also one of our 11 national UTC TriDurLE site directors. Dr. Pantelides' research interests include seismic design and rehabilitation of reinforced concrete, precast and pre-stressed concrete buildings and bridges, and the application of fiber-reinforced polymer composites. Dr. Pantelides' talk today is entitled Axial Compression Capacity of Concrete Columns Reinforced with Corrosion-Resistant Hybrid Reinforcements. If you have questions during the webinar, please type them into the chat room, and Dr. Pantelides will address these after his talk. Thank you, Dr. Pantelides, for speaking with us today, and I'll turn the meeting over to you now.
Thank you, Cheryl, and thank you, Shen-Ming. I also want to say, may Wahid Uddin's memory be eternal. So today I will talk to you about concrete columns reinforced with corrosion-resistant hybrid reinforcement. Before I start, I want to acknowledge my students, John Wright, who's in Richmond, Virginia, and Michael Gibbons, which is Vector Structural Engineers in Phoenix, Arizona. So a leading cause of reinforced concrete bridge rehabilitation is the corrosion-induced damage and spalling. So as you can see in this picture from Salt Lake City, actually from some years now, from a bridge, which I took myself, the presence of cracks and the ability of chlorides to permeate the concrete allow these chlorides to reach the reinforcing steel and so compromise the corrosion resistance of the concrete. So options for corroding reinforced concrete bridges include, as you know, cathodic protection with a press current, cathodic protection with galvanic systems, and corrosion passivation by electrochemical treatment. Here, I'm going to show you today some alternative reinforcement options for new reinforced concrete bridges. So the reinforcement will result in both initial and life cycle cost savings, as it will eliminate the need for replacement and could provide over 100 years of service life with minimal maintenance. So in this talk, I'm combining these two students' work and something called hybrid reinforcement for new concrete columns, which means glass fiber reinforced polymer. This could be in the form of a spiral or longitudinal bar. 2304 duplex stainless, which also could be in the form of spiral and longitudinal bar, and 316L stainless clad longitudinal bar. We were not able to obtain this stainless clad in a spiral. And of course, we have all carbon steel bars. So first, for those who are not familiar, glass fiber reinforced polymer spiral and longitudinal bars. So this material has been used in structural applications in both straight and fabricated bend form. It's a lightweight fiberglass rebar. It's a composite of fiberglass roving and resin that's impervious to corrosion. This is ideal for structures exposed to de-icing salts, seawater, other corrosive agents, weight or thermally sensitive projects, and projects that require electromagnetic neutrality. Actually, this last one was one of the first reasons this Aslan 100 fiberglass was used. So this Aslan 100 is stocked in 20 and 40-foot lengths from number 2 to number 8, and also number 10 diameter bars. Number 11 to number 13 diameter bars can be made to order. Here you can see a cast-in-place GFRP reinforced concrete deck. So what are the properties? We've tested them. The ultimate tensile strength is 725 megapascal, is a linear elastic material. Ultimate tensile strain 1.6%. And the compressive strength, we measure it indirectly, about 49% of the tensile strength. And the way we did that is we measure it by averaging the strain gauge readings from the vertical bars in the compression test of our column specimens. Measure compressive strain about 0.8%, elastic modulus 46 gigapascal. So here you see some work we did earlier on precast concrete bridge deck panels reinforced only with glass fiber reinforced polymer bars. Later on, this work took form of an actual bridge on US 6 near Price, Utah. This was a precast panels. To give you an idea, these panels are about 45 feet long and 7.5 feet wide. And these were reinforced only with fiberglass bars. These glass fiber reinforced polymer bars were then, these panels were then put on trucks and driven 130 miles to the site. You can see these panels being lifted where they were cast and being dropped on top of the bridge girders, just regular ASHTO type girders on this bridge on US 6. This bridge, by the way, has been in service now for 10 years with no sign of corrosion or any other degradation. Some work we did more recently involved glass fiber reinforced concrete slender columns. These columns were 305 millimeter diameter, about 3.73 meters tall. Here you see we wanted to be slender. In fact, we wanted to simulate buckling of these columns, and we were able to do that. And you can see here what I mean by hybrid, perhaps for the first time. It means that we have steel vertical bars and fiberglass spirals. In addition, we can have all fiberglass reinforcements, spirals and verticals. And here you see some kind of a hybrid, but with two layers of spirals. Both are fiberglass, and there is vertical bars that are fiberglass and vertical bars that are steel. So here it shows you the first study, the initial study we did for corrosion. This is the study that Mike Gibbons was involved. You can see these columns are 254 millimeters diameter, 711 meters tall, and this is all steel. It's all carbon steel reinforced. You can see 4 13 millimeter steel verticals and 10 millimeter steel spiral at 76 millimeter pitch. This is a hybrid reinforced concrete column, so I'm going to try and use some color to help you. So GFRP spiral will be from now on orange because it looks like it's orange, even though it looks a little more white. But in any case, here you can see a column that has steel verticals and fiberglass spirals with the same dimension. Here is one which is all GFRP reinforced concrete columns. That means everything here is fiberglass, the verticals and the spirals. So the intent of this first study was actually to see the corrosion performance of both the all fiberglass, the hybrid columns with the fiberglass spiral, and the all steel columns. So we used the Florida method of test for accelerated corrosion using impressed current. And you can see here, half of the column is immersed in water, the other half is in the air, and we're passing direct current. So here's the corrosion built up and the crack pattern after 11 weeks. You can see on the left here, this column has fiberglass spiral and steel vertical, and you can see practically no cracking. And these other two are the ones that are reinforced only with steel. They're all steel ones, carbon steel. Here you can also see that the carbon steel actually has a lot more current through it, whereas the hybrid actually doesn't let any current come through. So after we did the corrosion test for about 11 weeks, we did axial compression tests. As you can see here, we put some steel collars to guarantee that fracture would happen in the mid height of the column. And here you can see the results. The results of the compression test also help you to see the corrosion inside. So this is all steel control. That means this was not corroded. And here is the all steel corroded. You can see that we can barely find where the spiral is. And of course, you can see clear signs of corrosion on the vertical bars. Here is a hybrid. The one on the left is a control. That means this was not corroded. And you can see we fractured the spiral hoops, and we can see the vertical steel is buckled. Here is the one on the right, and this is the interesting one. This one was subjected to corrosion. You can see there's very minor corrosion here on the vertical bars. And again, the failure is very similar to the control. We have fracture of the spiral hoops and then buckling of the vertical bars. And here is the one that's all fiberglass. This is the control. And in this first series of tests, we didn't try to immerse it in the water. We knew it wasn't going to corrode that much. But in the second study, actually, we did immerse it. And again, you can see fracture of the spiral and some fracture in the verticals as well. So in the second study, we thought we'll use some new materials. This is a Knox stainless clad rebar. This is available only as a longitudinal bar. It's 316 stainless clad. And you can see the inside core of this bar is actually carbon steel, but the surface is actually stainless. So this is the Knox is a stainless clad carbon core, which is hot rolled to produce a very good bonded steel. There's a good metallurgical bond between the core and the cladding because of atomic interdiffusion. into stainless cladding and vice versa. It's a common interface, as you see over here. And this bond has both materials in the lattice structure and grows during hot rolling and spans some 110 microns or 0.11 millimeters in the finished product. So this is some kind of a new material at the interface, which is actually stronger than stainless steel itself because of the stronger carbon steel atoms now it contains. So we tested these stainless clad bars, ultimate tensile strength 715 megapascal. Ultimate tensile strain, though, unlike the fiberglass bar, is 23%. So this one has a yield strength of 500 megapascal at a yield strain of 0.25%. Elastic modulus is 200 gigapascal. So it's definitely a ductile bar. And the third product we used was the stainless steel rebar. This is available from number 3 to number 10. Produced in several alloys. We use the DX2304, which combines low nickel content with high mechanical strength. In the US, this stainless steel bar is available in grade 60 and grade 75. So we tested this once as well, the 2304 duplex stainless bar and spiral, ultimate tensile strength 790 megapascal, a little less capacity, but still plenty, 20%. Ultimate tensile strain, yield 660 megapascal, yield strain 0.33%, and elastic modulus 200 gigapascal. So then we constructed a typical column specimens similar to the one we had done before. The diameter of the column was the same, but the diameter of the spiral 305 millimeters. But the diameter of the spiral varied a little bit because we used a little larger fiberglass spiral compared to the metallic spiral. Metallic spiral here is only the stainless steel bar. The stainless clad bar does not exist in spiral form, only longitudinal form. So then I know I'm going to throw you a lot at you in this presentation. So to help you understand this, first of all, I have a reinforcement location. X means vertical bar, the first number. Y means spiral. So the reinforcing material can be either fiberglass, which is orange, stainless steel, which is the purple, it's solid stainless, and the stainless clad, which is black. This is the one that has the stainless cover. So the combinations we use is GN, which means fiberglass vertical bars with stainless spiral, NG, which means stainless vertical with fiberglass spiral, CG, which means stainless clad vertical with fiberglass spiral, and GG, which means fiberglass vertical and fiberglass spiral. So here you see the 4 combinations. We can call these hybrid, except the last one is all fiberglass, so it's not a hybrid. So the first one, you see the GFRP vertical and the stainless spiral, and the other 3 all have fiberglass spirals. So it's the NG, which is stainless vertical and fiberglass spiral, stainless clad vertical and fiberglass spiral, and then all GFRP spiral. Here, the stainless clad, you can see at the end, we have actually some protective caps, so the corrosion will not go through the section where the black steel is exposed. So here is the test matrix. We had about 2 specimens for R means corroded, except one series. This is the GN series. And then 2 control. For the stainless clad, we had 1 corroded and 2 control. For the all stainless, we had 2 corroded and 2 control. And for the all GFRP, again, 2 and 2. So I mentioned earlier that the bar diameter was a little bit different. So for the vertical GFRP, we used 13 millimeter, and all the rest was 16. And then for the spiral, that meant that the diameter would be a little bit bigger. We use 16 because the spiral with the fiberglass, the modulus is very low, it's about 1/5 that of steel. So we know we need a bigger diameter of the spirals, we get the same confining pressure. Stainless, of course, is just a 1/2 inch diameter. So here are some of the results. What happens after 60 days of corrosion? This has the fiberglass verticals, and it has a little bit more corrosion because this is the stainless spiral. The target current density was 2.2 microamperes per millimeter square, which we actually hit it pretty well. This is the clad vertical with the fiberglass spiral, and this is the stainless vertical with the fiberglass spiral. You can see these two are pretty similar. So then we did the axial compression test, and we put some carbon fiber wraps and the steel collar so the failure would be in the middle. I have a little video here. I will show you some of it. And we had some visitors from the main office, the staff who came to see finally how we break these things. These are early minutes for this test, which lasts about 6 minutes. And you can see here the spalling that happens. It's a very slow rate, 2.5 millimeters per minute. But you can see this is one of the hybrid columns with the fiberglass spiral. And you can see this starting early here. And then this next one, actually, I'm going to play it. It's a little loud. This is where the spiral fractures. And you can see the fiberglass spiral and the verticals. This has the clad verticals. And the axial load here in this test was, the capacity was 715 kips, 3,180 kilonewtons. And you can definitely see the discoloration of the spiral, but it seems like the clad bars are holding pretty well. So here are some results for all 4 different types of the specimens. So you see there is some damage, significant damage actually, for the stainless steel spiral, which may be surprising, but even stainless steel actually can corrode, as you can see here. Here you can see staining on the fiberglass spiral, even though the vertical is supposed to be stainless, but actually after 60 days, it did corrode some. Here you see this is the one that's all fiberglass reinforced, and you can definitely see no staining anywhere because it doesn't corrode, but that doesn't mean it doesn't suffer from water damage. We'll come back to that in a little bit, and definitely you see the fracture of the spiral. And this last one is actually the one with the clad vertical. This is similar to the video I showed you. And there is some staining here as well as staining byproduct of the fiberglass spiral. So here is the force displacement behavior of these columns. This one has a fiberglass spiral. That's actually fiberglass vertical, excuse me, with the stainless spiral. And you can see this is pretty ductile. The axial displacement was about 40 millimeters before failure. Now the orange here shows the corroded, and you can definitely see some reduction in the peak load capacity compared to the control ones. The control ones are green. So here's one with the fiberglass spiral and the stainless steel vertical. And again, you can see that the corroded have a little bit less capacity than the control. But the definite thing you see here is that the displacement, the axial displacement, is almost significantly less, almost half, compared to the specimen with the stainless steel spiral. And we expected this because the stainless steel spiral has a much higher tensile strain capacity than the fiberglass spiral. This is the all fiberglass, and something we didn't expect, we actually see some drop in the peak load capacity and the displacement capacity of the ones that were exposed to water, which means even though this is all fiberglass, it seems like the water actually can do some damage to the fiberglass. And this is the one with the clad vertical and the fiberglass spiral. And again, we see a little bit of influence of the corrosion, but definitely these three types with the fiberglass spiral barely reach 20 millimeters of axial displacement, whereas the one with the stainless steel spiral reaches almost twice that. So the displacement capacity of the stainless spiral is very obvious. Here's a comparison of all the control columns, including all four different types. And you can see again, the ones with the spiral, the stainless spiral actually displays quite a lot. As far as the peak load, I mean, they're all pretty much in the same range. Perhaps the ones with stainless verticals do a little bit better than the others, but pretty much in the same ballpark. And then here you can see the ones with the corroded, the ones exposed to the water. They all drop actually compared to their control counterparts. But again, we see that the one which has the stainless steel spiral actually is the more ductile of the specimens. So some conclusions, early conclusions of this study, we just completed it. So the failure mode for the all steel control columns was buckling of the vertical steel bars. For the corroded all steel columns, the failure mode was fracture of the spirals and then buckling of the vertical bars. Failure mode of hybrid columns was buckling of the vertical steel bars, but for a smaller length relative to the all steel columns, and tensile rupture of the fiberglass spirals. Failure mode of the all fiberglass columns was buckling and compressive rupture of the vertical GFRP bars and tensile rupture of the GFRP spirals. The hybrid control columns and the all GFRP columns achieved about 87 to 84% of the axial load capacity of the all steel control columns. This is an important conclusion because actually all steel is, as you know, a little bit less tensile capacity than fiberglass. On the other hand, fiberglass is very brittle. I mean, less than 2% strain. So this kind of result makes sense. And also, as I mentioned, because of the spiral having very low modulus of elasticity, about 1/5 that of black steel, you need to actually put more material, a bigger spiral, to achieve the same capacity as you do with the all steel columns. Of course, another thing you can do is also reduce the pitch, the spacing between the hoops. So for corroded hybrid columns with GFRP spirals, there was no visible actually detrimental effects to the carbon steel bars. Most of the corrosion observed in the all steel reinforced columns occur in the carbon steel spiral. So the fiberglass spiral increases the protective barrier to the all steel vertical bars. And it goes like this. If your spiral, which is on the outside of the reinforcement, doesn't corrode, then how are the chlorides going to penetrate and find the vertical steel bars? It makes it more difficult. It's a barrier, and then there's no byproduct. So the cover actually stays pretty intact, as I showed you in the picture. So there's no initial spalling. If there's no initial spalling, then the vertical bars are somewhat protected. Now, I can't say that it will happen like that for eternity, but at least for this accelerated corrosion test, which produced so much corrosion in the all steel carbon steel bars, it seems like it helped, at least for 11 weeks. So the hybrid columns are more ductile than the old GFRP columns. We saw that. The stainless spiral with the fiberglass vertical bars was the most ductile. The failure mode for the hybrid columns with the fiberglass spirals was tensile fracture of the fiberglass spiral and crashing of the concrete once it was no longer confined. The failure mode for hybrid columns with GFRP spirals was tensile fracture of the fiberglass spiral and crashing of the concrete once it was no longer confined. The failure mode of the hybrid columns with the stainless spiral and the fiberglass vertical bars was fracture of the fiberglass vertical bars in compression but the columns actually still retain strength and did not fail suddenly. So the stainless steel spiral gives the more ductile response. However, even the stainless steel reinforcement, we saw they are sensitive to uneven concentration of pitting corrosion, which can lead actually to axial compression capacity reduction due to the localized section loss. That was something that surprised us. Degradation of the stainless clad vertical bars due to this saltwater exposure was minor, and the submerged columns with stainless clad vertical bars and fiberglass vertical bars had no appreciable drop in axial load capacity. Degradation of stainless steel spiral due to this water exposure exists, and the submerged columns with stainless steel spiral and fiberglass vertical bars had about a 3% drop in axial load capacity. The degradation of the stainless vertical bars due to the saltwater exposure exists, and the submerged columns with stainless steel vertical bars and fiberglass spirals had about a 4.5% drop in axial load capacity. So we also saw that GFRP reinforcement can degrade in saltwater exposure, and these all fiberglass, both verticals and spiral columns, had about a 6% drop in axial load capacity. So comparing these two studies, the experimental results from the previous study are comparable, where we had compression capacity reduction of the all carbon steel columns ranging from 13 to 24%. You would expect that because even the mass loss range from 16 to 18%. But the compression capacity reduction of the hybrid specimens with the all carbon steel vertical bars and the fiberglass spiral was about 5%, and the corresponding mass loss was 7%. So obviously we use a very small number of samples here, and there needs to be more extensive research, and also for larger column specimens. And specimens that seem promising is the ones reinforced with stainless clad vertical bar confined with fiberglass spiral. Of course, we also need additional research regarding the performance of such columns, not only under axial loads, but also under lateral loads, cyclic loads simulating earthquakes. So these are the references that I included in this paper. It's mostly myself and my students because that's what I presented here. And these are the sponsors: Utah Department of Transportation, New York State Department of Transportation, Hughes Brothers, who provided the fiberglass, Outokumpu Stainless USA, who provided the stainless steel, and Knox Stainless Steel Clad Rebar, who provided the stainless clad bar. So I want to thank you, and I want to take your questions, and I'll leave you with this quote that Democritus said many years ago: everything existing in the universe is the fruit of chance and necessity. So I want to thank you for your attention.
Thank you, Chris. We really appreciate your talk. I have welcomed anyone to type questions into the chat room if you have questions. I don't see any at the moment. I've also added your email address there in case anyone has questions that they think of later that they would like to ask you.
Thank you, Sharon.
So we'll wait a minute just in case anyone has questions. If not, I just want everyone to know that this webinar is being recorded and will be posted on our website in just a few days. So if you missed a part of it or all of it, feel free to go to our website. Dr. Shi has put the email or the URL in the chat room for those of you who don't know where that is at.
Hey,
so we'll just
Sharon,
wait. Yeah, yes.
can the audience unmute themselves, or can it, I mean, is there an option for them to unmute and talk, or they can only type in the questions? Oh, I already see one question in chat box. Maybe I can read it for you, Chris.
Okay.
By the way, yeah, very good presentation.
Thank you.
What is the main reason for FRB bars to deteriorate, and what kind of reactions does it have?
So these fiberglass bars, the way they're made, they're pultruded. So what happens is the dry fiber is on a spool. Actually, I went to Nebraska where they make them, so I know how they make them. And it passes through a resin bath. So the resin bath actually, after it goes through there, they cook it. They put it in high temperature for half an hour, like 400 degrees Fahrenheit.
Epoxy, or what kind of
resin?
resin?
It's epoxy. It's
okay.
Epoxy resin. So I think what happens is the epoxy resin starts to degrade the bond of the fibers with the resin. After you expose it into water, there must be some, I don't understand the exact chemistry of it, but I think the water somehow will infiltrate and start breaking the bond.
Yeah, actually, well, my previous life was a polymer chemist. So epoxy resin does get brittle, especially under UV light and under water ingress. Yeah, they become less reliable.
Yeah. But it was a surprise to us because it actually, we saw about a 5% drop in the axial capacity.
Well, while we're waiting for other questions, I actually have some questions for you. Again, very interesting presentation. And, you know, in terms of the water damage, I guess, do you think that has anything to, I guess, I mean, is there any way to mitigate that? Like maybe by design it differently or fabricate it differently?
I'm sure there are better resins that could be used, Xianming. I mean, I'm familiar, for example, in carbon fiber polymers for retrofit, which I'm more familiar actually. There is a resin which can be made, phenolic resin, to protect the fibers from fire. So if there is such a resin to protect from fire, I would assume that people will come up with different resins to actually protect from water. However, I use the product which is available commercially, and it's used quite a bit. I showed you the bridge deck that we built here in Utah, and it's still up there after 10 years. And there's no sign of it, any degradation. In fact, no corrosion, no spalling of concrete, nothing. So I think this accelerated corrosion, you have to understand, is very aggressive, very aggressive. I mean, it could happen to an actual column to be in salt water for that long, but I think it also has to do a lot, as you know, Xianmin, with the concrete. I mean, the concrete we used was very normal type concrete, 4,000 psi. So
yeah,
very difficult to say. I think it's possible to protect it, but I didn't use anything that's protected. I just use whatever I can get on the market.
Yeah, the most commonly used ones.
Most commonly used,
yeah. Here's another question from the chat box. Which reinforcement is more cost effective?
So that's a very good question. I think the stainless steel bar is quite expensive. I priced it, and it's probably 2 or 3 times more than the fiberglass. The fiberglass for a number 5 bar that we used was about $1.25 per foot, which competes rather well with epoxy coated bars, for example. Now, the one I couldn't find the price because they donated the material is the Knox, the clad bar. That clad, stainless clad bar has a big promise because, first of all, most of the bar is black steel in the center, as I showed you in the picture. And actually, only the cladding is stainless. And that one in particular was worrying to us, especially at the ends of the bar where I showed the little cups. And we just epoxy those caps on. There's a special tool actually you can use to put those caps on, and we didn't have it. But even with that effort, it actually protected the bar. So the ones that were the least affected, it seems, was the stainless clad bars. And those are much cheaper, I would think, although I don't have numbers in front of me, than the solid stainless, because The stainless part is only a few fraction of a millimeter. So I think those are the most, to answer your question, those are the most probably efficient economically.
Yeah, they actually use that kind of technology in doll bars as well. It's just a thing, stainless steel clad, and most of the, core is still black bar. So
Yeah, but
carbon steel.
it performed rather well.
Mm.
It seems like that one protected the black steel inside from corrosion.
Yeah, I guess it has a lot to do with your intended application and intended service environment and life cycle cost analysis and all of that.
Right, and I have to admit that 60 days or 7 weeks may not be enough, but it was enough to corrode the black steel. So I can't imagine it's not severe enough.
Mm-hmm. Actually, I have one maybe last question for you. Okay. Before I do that, here's another one from chat box. Right. I'm not familiar with the accelerated corrosion test, but could that be the reason for FRP to fail?
No, I don't think so, because actually we didn't impress a current into the fiberglass bar. Mm-hmm. And it didn't fail. I mean, let's be honest, if you're only dropping the axial load by 5%, 5.9%, that's not failure. I mean, the failure would have happened anyway, as we showed using the control. I mean, the control columns also, the fiberglass failed because we're putting 700 kips of axial load. That's a lot of axial load, like 3,500.
Yeah, I think the moisture damage or water damage is most likely, yeah.
Yeah, it was moisture.
Okay, the next one, actually from Steve Nolan. Aslan 100 is made with a vinyl ester resin package, not epoxy. STM D7957 has moisture absorption and age conditioning protocols. Both ACF 440 and ASHTO guide spec have environmental reduction factors up to 30%. So the minor loss of strength is very conservative compared with the design guide.
That's true. That's true. It's vinyl ester. I'm sorry, it's not epoxy. Steve, thank you for that. Yes, and yes, there are many reduction environmental factors in the design of new structures with fiberglass bar. And yes, you can find those in 440. So yeah, what we saw here is very typical.
Yeah, I would imagine even with the polyester, yeah, you still got moisture damage. Yes.
Yes, I think so.
But it's kind of interesting because, well, they're basically protected from UV, so there's no UV aging, I assume, unless it's, during construction, they're exposed to UV.
Yeah. During construction, actually, they took care of that. They covered them.
Okay. So, yeah, my last comment or question was on the section loss. You mentioned section loss, for this, possible reason of stainless steel, reinforced one seeing significant drop in mechanical properties. Did you actually measure the section loss or mass loss, or because I see you mentioned?
No. We just use from the current and the voltage. We use Faraday's law.
Oh, I see. Because I would argue, as a corrosion scientist, I guess, it's actually more than the section loss. Sometimes, because your localized corrosion creates so much buildup of the corrosion products and tensile stress and bond loss, and
yes, so you're right.
May not be entirely section loss.
No, it's not very significant. In fact, that's one of the conclusions. I didn't put it up there because I didn't want to focus on this part. Because the pitting corrosion was more severe actually than section loss because, as you said, it's concentrated.
Yeah, that's the tricky part. I mean, the risk is really hard to predict or prevent because it's so localized and stochastic in nature.
Yeah.
Well,
so it's interesting because nobody had tried these different combinations of hybrid reinforcement.
Oh yes, actually talking about that, I saw one comment you had was like for the one with stainless steel and carbon steel, the corrosion was mostly seen on the carbon steel. That's not a surprise because it's galvanic corrosion. This basically forms a battery where the carbon steel tends to sacrifice itself to protect the stainless steel, which actually doesn't need any protection. So that's a typical galvanic corrosion scenario.
Yeah.
But you, Chris, you did say the marriage between the stainless steel and the GFRP was probably, I mean, in terms of both the corrosion resistance and then the toughness or ductility.
Yeah. I think that one is interesting, and there are some more interesting things I didn't show here, which make me feel hopeful for, let's say, seismic performance.
Mm-hmm.
Because fiberglass, actually, even though it's an elastic material, and I'll go back and show you at least this one picture. It tends to want to come back to vertical, to recenter itself. For example, in this test of a slender column, you can see here on the right, this is right about to fail. And of course, the way it fails, you get compression here, failure of the concrete. But the reason I put this picture here is after it buckled, a very nice sine wave, we removed the axial load. And guess what happened? The column came back to vertical because you know what? The material is elastic. The fiberglass wanted to go back to their zero position, right? And so it's kind of a self-centering mechanism if you have fiberglass bars. Of course, most bridge engineers would be worried that this is very brittle failure. But of course, you can design so it doesn't fail brittly, And I think in a seismic situation, this would be a very nice thing to explore, that the fiberglass bar actually wants to come back to vertical after an earthquake.
So maybe with a little bit of self-healing or whatever, this could achieve a fraction of the original load bearing capacity. I mean, if we reload.
Yes. I think that could be another opportunity here. The main reason we use the fiberglass spiral is because we believe it protects the vertical steel from corrosion. Because corrosion, as you know, will have to come from the outside, right? And in my belief is that if you have the fiberglass protecting the vertical steel, it's much harder to get the chlorides to attack it. You're actually creating an extra barrier for those chlorides to go in. And even if they go in and they attack the vertical steel, the byproduct is probably not going to push out the concrete, the volume expansion that you normally see in all steel reinforced columns.
Yeah, I'm a little bit curious about the chemistry of the interface, because you're talking about glass, which may actually chemically react with the adjacent cement paste and make the bond stronger. I mean, versus another scenario where you have carbon fibers, which are basically inert, and they're not even hydrophilic, so they don't really bond that well with the cement paste.
Right.
I'm just guessing.
But one thing about that, Xianming, is that carbon is very expensive. They told me in no uncertain terms they wouldn't use carbon for new construction.
Yeah, I understand. And my point was actually glass might be better than carbon in this scenario in terms of reducing the ingress, because if your interface has no ITZ or interfacial transitions or a weakness or
Yes.
pathway for moisture and chloride to go through.
Right. And another thing about carbon and touching steel, I think it may actually, what you mentioned earlier, it might accelerate the corrosion.
That's a debatable one because there are different. I've seen different publications. Some say the fiber is actually beneficial. Some say it's detrimental. So, yeah.
I'm familiar with, for example, carbon fiber polymer sheets. When we retrofit a bridge, we try to stay away from metal. We try to separate them.
Yeah, you're right. Yeah, the metal could be sacrificing itself to protect the carbon, which basically pumping electrons to the carbon.
Right.
Interesting. Okay.
All right. Well, thank you very much for coming, and appreciate the questions.